So the continuation of chapter 4, that is inverter. In the last session I discussed about what exactly parallel inverter. Then you go for another inverter circuit that is important for competitive point of view. That is, I am discussing a single phase current source inverter. Okay, first we will start with what exactly a single phase current source inverter. Yes, all of you write down. A single phase current source inverter. The current source inverter. That you concentrate. Already in the starting of inverters concept, I already discussed what the difference between voltage source inverter and current source inverter. Here, so many points I given with respect to current source inverter and voltage source inverter. Here, one or 2 points once again I am giving here with respect to current source inverter. That is a single phase current source inverter in the sense this is CSI. CSI or CFI. Current source inverter or current fed inverter. That is, in current source inverter, input current is constant or adjustable. That is, input current is constant or adjustable in the case of current source inverter. That you know. But point to remember, whatever the output current is there in current source inverter, output current amplitude and waveform independent of load parameters, but output voltage depends on load parameters. That is, output current and waveform in current source inverters. Output current amplitude and waveform. Independent of load parameters. Independent of load parameters. Independent of load parameters. But output voltage depends on the load parameters. But output voltage depends on load parameters. Depends on load. Okay. Depends on load parameters. This you know. Input current is constant or adjustable. Output current amplitude and waveform independent of load parameters, but output voltage depends on load. Based on the load, only voltage waveform will be changes, but current waveform remains same. Yes. In current source inverter means input is stiff DC source or constant current source. Stiff DC source or constant current source. Then we can adjust that current also. Input side we can adjust that current also. By adjusting the input current, then we can adjust the output current. But that output current is independent of load parameters. If you want to adjust the output current means we can adjust the input current. Then only it is possible. Understood? Then in current source inverter, I am talking about current source means we don't have practically current sources. Then if you want to make current source means a voltage source in series with large inductor acts as a current source. That's why a current source inverter must be consist of one large inductor at input side to maintain ripple free DC current. In order to maintain the ripple free current, it contains a large inductor at input side. That point you know. Okay. Then what is the applications of this CSI, current source inverters? What are the applications of current source inverters? Applications. So many applications are there. One is speed control of AC motors. Speed control of AC motors. Speed control of AC motors. Then used in induction heating. Induction heating. Used in induction heating. Okay. Lagging wear compensation. That is reactive power compensation. Lagging wear compensation. Lagging wear compensation. Then starting of the synchronous motors. Starting of synchronous motors. Synchronous motor. Okay, this about some of the applications of current source inverter we are using. We know that these inverters are more favorable for regenerative applications. Okay, that you know, these are used for regenerative applications. Okay. These are used for regenerative applications. So many differences are already given. Regenerative application. But in current source inverter, we don't have any feedback diodes requirement that I discussed already. Okay. Now this is some introduction to the current source inverter. Here I want to discuss a single phase current source inverter with ideal switch arrangements. Then for resistive load and capacitive loads that I want to discuss. But point to remember, the current source inverters are more preferable with capacitive loads instead of using inductive loads. Current source inverters are more preferable with capacitive loads. CSI is more preferable with capacitive loads. More preferable with capacitive loads. Capacitive loads. More preferable with capacitive loads. Okay. Then we will see what is the circuit we are using for single phase current source inverter. This is the circuit we are using. Practically we don't have any current sources. A voltage source in series with large inductor. It acts as a one current source. Let this is I. This is L. A voltage source in series with large inductor acts as a current source. In current source inverter, we don't have any feedback diodes. We are using only main switches. That means in CSI, the devices which withstand the reverse voltage, those devices are more preferable. The devices which withstand the reverse voltages, those devices are more preferable. This is Vs, this is T1, T3, T4, T2. Okay, I'm explaining the first concept for resistive. This is R. This is the polarity of load current. This is the polarity of load voltage. This is acts as a current source. A voltage source in series with a large inductor acts as a current source. And it acts as a current source. This is acts as a current source. That point to remember. This total is current source. Okay. This acts as a current source. Now, first is a concept for purely resistive load. Then how this circuit will convert DC to AC, DC current to AC current. Okay. Now, here whatever the switches we are using, the switches are the devices which having the reverse blocking capability. Those switches are preferable. Okay. I told already, BJT, MOSFET and directly we cannot use. By using some series diodes only, these are preferable. And GTO is not preferable because if it is very less voltage rating requirement is, then GTO is preferable. Once we are using high power applications, means that GTO is not preferable for current source inverter, is not used in current source inverter. But simply remember, the devices which withstand high reverse voltages, those devices are more preferable for current source inverter. Now see, I want to explain the circuit operation for resistive load. Here we can turn on these switches in such a way that we want to convert DC to AC. We can turn on these switches in such a way that we want to convert DC to AC. How it is possible, that we will see. Let for 0 less than or equal to t less than or equal to t by 2. Yes, this I am explaining for resistive load, R load, purely resistive load. For 0 less than or equal to t less than or equal to t by 2. Tell T1, T2 is on. I trigger the T1, T2. On and off is in your hand. Based on your requirement, we can make T1, T2 is on or T3, T4 is on. If T1, T2 is on, what is the equivalent? That you will see. If T1, T2 is on, this is current. This is T1, T2 is on. This is load. Then this is T2. This is equivalent circuit. This is T2. That this is assumed current direction. This is assumed load polarity. Tell, if T1, T2 is on, the direction of current, this is the current supplied by the source. This is the direction of current. This positive polarity is connected here. This negative polarity is connected here. That means I0 equal to plus I. Then V naught equal to plus Vs. Okay. But I'm telling that if you take, instead of not consider voltage, because you assume that it is a current source, means I naught equal to plus I. I naught equal to plus I. Understood? Now, if T1, T2 is on, load is subjected to positive current. Load is subjected to positive current. So, okay, this is the polarity given for current and this polarity given for voltage, and this is the direction given for load. Then if you take this current direction, same that of load current direction, that's why you take I naught is plus I. Then for T by 2 less than or equal to T, less than or equal to T. Now what we can do means, now we will turn on the T3, T4. T3, T4 is on. That means T1, T2 is turn off by using some commutation circuit. What type of that commutation we are using, all this later on we will see. Okay, this I turn on that T1, T2 using some commutation. Then if T3, T4 is on, what is the equivalent? If T3, T4 is on, this T3 is on, this is pure inductor, large inductor, this is I, T3 is on, S, this is T3, and this is load. Load is connected like this. This is load, and load is connected. This is T4 is on. This is I. Actually, this is the assumed current direction, I naught. This is R. Now tell me, if T3, T4 is conducting, what is the direction of current? If the T3, T4 is conducting, this is I. Then exactly opposite to assumed load current direction. Then what we can get? I naught equal to minus I. I naught equal to minus I. If T3, T4 is conducting. That's why we are converting unidirectional current into bidirectional current in such a way that we are converting DC to AC by triggering T1, T2 and T3, T4. Okay. That's why it converts DC current into AC current. That's why it acts as a current source inverter. Now, with this, if you draw the waveforms means, in this case, if you draw the waveforms means, then what we get? This current source inverter, we are drawing the waveforms for purely resistive load first. For current source inverter, I am drawing the waveforms for purely resistive load. That this is T. For 0 to T by 2, they are getting plus I. For T by 2 to T, we are getting minus I. Again T by T2, T2, 3T by 2, we are getting plus I. Like this we are getting the cut waveform. But this waveform we are drawing for which load? Resistive load. For R load, this we are drawing for R load. We know that for resistive load, voltage and current waveforms are same. This V naught and I naught is same for resistive load. This is plus I and this is minus I. Here T1, T2 is conducting. Here T3, T4 is conducting. again T1, T2 is conducting. This is T by 2 and T. Like this we are converting into DC current to AC current and we are getting the square waveform. Okay. This about current source inverter. For resistive load voltage and current waveforms are same. Okay. But we know that this for our load, voltage and current waveforms are same. Okay. Voltage and current waveforms are same. Current waveforms are same. Voltage and current waveforms are same for our load. Yes. Now tell. And in current source inverter, we are not using any feedback diode. If you want to draw the waveforms for remaining loads means, I told already, whatever the load you are connecting, the output current waveform is independent of load parameters. Once we are generating this square waveform is remains same. Then based on the load parameter, which waveform will be changing? Voltage waveform is changing because it is a CSI. Now I want to draw the voltage waveform for different loads. Here I am considering only for purely capacitive load only I am drawing the waveform. Now see, now if you want to draw the waveform for any other loads, that means for any load, current waveform is remains same. Current waveform is remains same. But voltage waveform is changes. Voltage waveform changes based on load parameters. Now you want to draw the waveforms for purely capacitive loads. I am drawing the waveform for purely capacitive load means I am drawing the voltage waveform. But what about current waveform? Remains same because of current source inverter. We are drawing the waveform for purely capacitive load. Now what is the waveform we can get for purely capacitive load? That you will see. Here we are drawing the V0 waveform. But remaining current wave, whatever the load you can connect, current waveform remains same because we are generating square waveform is that is remains same because it's a current source inverter. Okay. Now, if you want to draw the waveform for C load means, for purely capacitive load means, one method is connect capacitor here, apply KVL, apply Laplace transform, apply inverse Laplace transform for different values of T, then you can draw the waveforms. That is one method. But it is a complex procedure or lengthy procedure. That's why you can analyze like this only. Purely capacitive load means how to write IC equal to C into dV by dt. The current through the capacitor is I equal to C into dV by dt. Tell 0 to T by 2. We can draw the voltage waveform in such a way that this condition must be satisfied. We can get the voltage waveform in such a way that we are supplying the, if T1, T2 is conducting, current is positive. If T3, T4 is conducting, current is negative. By satisfying that only we can get the voltage waveform. Then tell me, 0 to T by 2, current is positive. Current is positive means dV by dt. Capacitance is always positive. Then what about dV by dt? dV by dt is positive. Then only current is positive. dV by dt positive means rising slope or falling slope? Rising slope. Now we can draw the voltage waveform in such a way that the dV by dt must be positive. But it is a capacitive load na. For purely capacitive load, what about voltage? Current leads. Current leads means voltage lags. Voltage lags the current by angle of 90 degrees. That means dV by dt positive means rising slope. Because of purely capacitive load, voltage lags the current by angle of 90 degrees. Then with that consideration, then you can draw the waveform. Then you can get the wave shape like this. This is dV by dt. Okay. Next. Again. From t by 2 to t, current must be negative. Current negative means, if you want to maintain negative current means, dV by dt must be negative. dV by dt must be negative means it is a falling slope or rising slope? Falling slope with 90-degree phase difference. Okay. Again rising slope. Again falling slope. Then you can get like this. This is the voltage waveform for purely capacitive loads. This is voltage waveform for purely capacitive load. That's why in current source inverter for purely capacitive load, the voltage waveform is triangular. See, in voltage source inverter for purely inductive load, current waveform is triangular. Here in current source inverter, voltage waveform is triangular. That you concentrate. This is T by 2. This is T. Understood? Tell me. Now I want to draw the input voltage waveform also. Actually input is current source now. Input is current source. But we are drawing with respect to input voltage waveform. Then what the wave shape we can get? Yeah. Then you can draw the Vn voltage. Tell. If T1, T2 is conducting, V0 equal to plus Vn. If T3, T4 is conducting, V0 equal to minus Vn. That means from this, if T1, T2 is conducting, the point to remember, V0 equal to plus Vn. Then T3, T4 is conducting, or Vn equal to plus V0, that you take. Vn equal to plus V0. T3, T4 is conducting. Then Vn equal to minus V0. If T3, you take, this is plus, this is minus. Then Vn equal to plus V0. Then this is plus, this is minus. This plus is connected here. Minus is connected here. Then Vn equal to minus V0. Vn equal to minus V0. Then with this, if you draw the waveforms means, here T1, T2 is conducting. Here T1, T2 is conducting. Okay. T1, T2 is conducting. Then Vn equal to plus V0. Vn equal to plus V0. If T1, T2 is conducting. So, okay. Now, we can draw this Vn waveform means, then how we can get? Vn we can get like this. Here T1, T2 is conducting. Here also T1, T2 is conducting. Okay. T1, T2 is conducting. This is T by 2. This is T. Then what you can get? You tell me. This is T by 2. You get the like this. Yes, this is Vn waveform. Okay. If T1, T2 is conducting, plus V0. T3, T4 is conducting, minus V0. T1, T2 is conducting, plus V0. This is Vn waveform. Then these are the waveforms in current source inverter, single phase current source inverter. This is for purely capacitive load, purely resistive load, and this is the Vn voltage. That's the input voltage waveform. Here I want to list out some points here. Tell me. During the operation of current source inverter for purely resistive load, for R load, here I am operating square wave inverter now, that I am writing like this. This is summary points. This is important for any competitive from the current source inverter. For R load, voltage and current waveforms are voltage and current waveforms. Current waveform is square waveform. What type of waveform we are getting? Square waveform. Is a square waveform. Is square waveform. Next. If you take for C load, for purely capacitive load, for C load, voltage is triangular waveform. Triangular waveform. What about current? Whatever the load you can connect, current waveform remains same. Current is square waveform. Square waveform. This is current is square waveform. Voltage is triangular waveform. Now tell me, what is the time taken to reach peak voltage? Time taken to reach peak voltage for purely capacitive load. Time taken to reach peak voltage. How much you tell me? T by 4. Peak to peak means T by 2. I am talking about peak voltage. Peak voltage in the sense you take references from 0. From this point to this point to reach this voltage, how much time it is taking? T by 4 time. Okay. And time taken to reach peak voltage is T by 4. Then you know that IC equal to C into dV by dt. IC equal to C into dV by dt. Then this is I equal to, IC means I, C into. If the voltage is changing from 0 to peak value, 0 to peak value in the sense Vp minus 0. How much time it is taking? T by 4. Then from this, what is the peak voltage? Peak voltage equal to I into T by 4 by C. In current source inverter, we are calculating peak voltage. In voltage source inverter, I calculated peak current. This formula for purely capacitive load. Then what is the nature of the input voltage waveform we are getting? Okay. Another observation here. Input voltage waveform is sawtooth. It is a sawtooth waveform. This is the sweep signal. That is in current source inverter for purely capacitive load, input voltage is sawtooth waveform. Sawtooth waveform. Next, one point to remember, in one cycle, the output voltage waveform we are getting in one cycle, the output voltage we are getting is one cycle only, that is F frequency. But what about in one cycle, the input is subjected to two cycles. In one time period, the output is one cycle. In one time period, the input voltage is two cycles. That's why, that means in one time period, output voltage frequency equal to F, because we are getting only one cycle. But in one time period, this is one sawtooth and this is one sawtooth. Then input is subjected to two cycles. Then input voltage frequency. How much? Input voltage frequency equal to 2F. Okay, this about what exactly current source inverter for resistive load and capacitive loads. This point to remember, in a voltage source inverter we are studying about purely inductive load. In current source inverter we are studying purely capacitive load. Where the current waveform is triangular, here the voltage waveform is triangular. Exactly opposite. This about the current source inverter. Okay. But point to remember, in current source inverters, there exists here we are using the thyristor is the switches now. Once we are using the thyristor as a switches means, in order to commutate those thyristors, then you must use external commutation circuit. In current source inverter, there exists two types of the current source inverters are operated based on either forced commutation or load commutated. That's why practically there exists only load commutated or forced commutated current source inverter. What you remember, practically there exist forced commutated or load commutated CSI. Forced commutated or load commutated CSI. Okay, load commutated CSI. The point to remember, if power factor is lagging, then we can use forced commutation. We can use forced commutation. If power factor is leading, we can use load commutation. We can apply the load commutation. If power factor is lagging, in the case of current source inverter, we can apply the forced commutation. If power factor is leading, then we can apply the load commutation. Okay. But in current source inverter, always current is unidirectional. But based on this average input voltage is positive or negative, the power is delivered from either source to load or load to source. Okay. That means in CSI, always I is unidirectional. Then based on Vn, input voltage. If Vn is positive, average Vn is positive. This I am drawing this waveform now. Average Vn is positive. Power is delivered. Source to load. If Vn is negative, if average Vn is negative, power is delivered load to source, then used for regenerative applications. And used for regenerative applications. Okay. This about in CSI always I is unidirectional, but based on Vn, average Vn is positive, power is delivered source to load. If average Vn is negative, power is delivered, that's what is this Vn value, negative. Power is delivered from load to source, then used for regenerative applications. Okay. This about what exactly? Current source inverter. This is the ideal case I am explaining. In this current source inverter, I am not representing any commutating elements, all these. I explain for resistive load and purely capacitive load. Here I am telling that in a current source inverter, there exists a load commutated current source inverters and forced commutated current source inverter. Now, I want to give some example for what exactly forced commutated current source inverter, that I want to discuss. If you use the forced commutation, how the forced commutation is? Mainly current source inverter means we are using the devices is thyristors. We also use other devices also. We can also use BJT in series with some diodes, MOSFET in series with diodes. If you are using those type of switches means no need of any commutation, because those are the self-commutated. When the commutation comes into the existence means once we are using the switch is the thyristor, because input is DC now. If you want to turn off the thyristor means compulsory we can use commutation. But here what I am telling, in a current source inverter there exists a forced commutated current source inverter and load commutated current source inverter. First I want to give what the example for forced commutated current source inverter, then what is the analysis of that forced commutated current source inverter, that I want to discuss. The another point you remember here, even though I am drawing the pure square waveform here, practically you don't expect pure square waveform. Even though I am drawing here pure triangular waveform here, but practically you don't expect pure triangular waveform. Compulsory there must be some distortion. But this is only ideal case waveform, ideal waveforms only. Practically the waveforms is distorted. Understood? Then during one cycle, during one time period, this output is subjected to a frequency, then input is subjected to 2f frequency. Input is subjected to 2f frequency. These points you remember with respect to current source inverter. With this, the fundamental concept of current source inverter and the simple current source inverter, how it is converting DC to AC is completed. In the next session, I will continue with this current source inverter. Then I want to give forced commutated current. One example I want to explain for forced commutated current source inverter. Okay, thank you. Concentrate on these waveforms. All these points you concentrate.